So let's see. 98, you've got your area, which is 60 minus x times x has to equal 800. FOIL it out. 60x minus x squared is 800, which means you have to know how to set that up. So we get x squared minus 60x plus 800. I just moved everything to one side. Bless you. I moved everything to one side to keep it positive, senor. This is 98, the first one, on the first page. Okay. And I don't know, do you want to try and factor what times what's 800 to add up to negative 60? Negative 40, negative 20? Hey, that was easy. So you have x minus 40, x minus 20. So you have two possible zeros then. Okay. Now, in order to figure out now which one of those is going to work, it goes to the second part. You only have so much fencing. Okay. They're donating the fencing. So if you used, what is it? You use the 40, it'd be 20 by 40. And if you use the 20, it would be 20 by 40. So that's possible. Your dimensions would be 20 by 40 as it works itself out. Okay. What's the next one on that one? I should have made this a little bit larger to read. I'm sorry. 100 on there, the home electronics. Manager of the home electronics store is considering replacing a new model of digital cameras. Hey, look, back in 2002, they had digital cameras. Did you know that? My first SD card, the little thumb drives. I found one, actually I bought it at a Home Depot of all places. It was a 128 megabyte, not like gigabyte, like megabyte. It held 24 pictures, maybe 25 pictures. Guess the price. About $60. It was a thumb drive. It cost about $60 for that thing back then. Think about the amount of memory you can buy nowadays for $60. It's insane. Stupid. Really? Well, here's the other thing. That calculator is $135. Guess how much it was back in 1992? $135. Shut up. All right. So here we're back to that one with the electronic stuff. Current price is $680. They sell 700 of each month. Sales data from other stores indicate for each $20 decrease in price, about 5 more cameras per month will be sold. How much should the manager charge for a camera to maximize monthly revenue? And then what is the what is that monthly revenue? So here's where you have your sales and your units. Okay? You have sales and units. When you do these styles of problem, I would recommend writing it like this. That way you can corral, if you will, the sales amount, and you can corral the number of units you sell. So sales, I'm talking about price. How much was the camera to start with? $680? At $680, how many units did you sell? 70, okay? So what I want you to think of here is that if you were to start to FOIL this out, 70 times 680 would generate your sales figure, how much money you sold. Does that make sense? That's where this is starting from. The next term they talk about units of decreasing price, how many more they would sell or whatever. But they said for every $20 decrease in price, they would sell, what, 5 more, was it? Yeah. Okay. Now, here's where it gets a little weird. This is where students have a problem with it. If I'm saying I'm deducting $20, if I put a value of x in there, if x is 1, how many times did it subtract $20? 1 time. How many times? If I did 3, how much money am I subtracting? 60. If I did 5, how much money am I subtracting? 100. That value of x is the number of times it's decreasing. That number x, the number of times decreasing, will also correspond to the number of times you increase your sales that many times over. So your increase in sales was 5x, I believe. I'm just guessing off the top of my head. This sets you up then as intercept form. When you have these sales in units things where what goes up must come down, it's an intercept form style problem, which means you can set aside equal to 0. If you wanted to FOIL this whole thing out and try to factor it, it works as well. But remember, when we're talking about this thing in intercept form, these two generate, I'm sorry, those are, bless you, those are my, bless you, those are my terms, and terms generate zeros. So if I set both of these terms equal to 0, I will figure out where it crosses the x-axis. So if I set 680 minus 20x equal to 0, basically it winds up, bless you, x will equal 680 divided by 20, which is what, 34? And I do the same thing on the other side. I'm going to get 70 will equal negative 5x, so it's be what, negative 12? 14, sorry. Good morning. So I have two zeros, negative 14 and positive 34. Remember what that means, what that looks like. And that's the whole idea with most of these, when you get to the sales quota thing, if you will. If you plot it via the zeros, just a rough sketch, knowing that you have a 0 at negative 14 and a positive 34. Those are zeros. What occurs at its midpoint? The axis of symmetry, right? Which then you can figure out the maximum. So what's negative 14 plus 34? 20. What's half of that? 10. So the midpoint between these two is at 10. 10 is the x value that generates the x coordinate for the maximum. Okay, so I should decrease my price 10 times 20. What's 10 times 20? 200. So that means I should sell them for how much? 480. I should sell them, if I decrease my price 10 times, I get 680 minus 200. I should sell them for $480. And if I do so, how many units will I sell? Very good. I'm going to sell 120 units because I know that I have 70 plus 5 times 10. I will sell 120 units at that. Now, what they're asking us this last little bit, though, is what's the maximum revenue? Well, multiply those two numbers together. Some number. 57,600. What these values mean, what you interpret the data here to be, is that this multiplier of x tells you how many times you're going to decrease your price, and that same multiplier is how many times you're going to increase the sales. If I decrease it 10 times, I increase my sales 10 times. That number remains constant. Okay? And that's where that comes from. So the prices that they're asking you is, what's the price you should sell them at? How many do you sell? What's your maximum revenue? Okay? Then, getting less foggy on that style, I hope? Okay. Yeah, you guys all fun. Let's see. 101, the Big Bertha Cannon. That one's straight calculator work. Did that make sense? Do you want me to walk you through the calculator on that one, or are we okay on that? Okay, we'll walk through the calculator. Okay. So anytime you get really crappy looking numbers, press a button on the calculator, okay? So make sure you got your calculators out, and let's do the Bertha Cannon. And you'll have to excuse me, mine takes a while to type in, so it's negative 0.0196 x squared plus 1.37x. Why is there no C value here? Okay. What is this problem talking about? The Big Bertha was a what? A cannon, all right? Where do you think the cannon was located? On the ground, probably underground, wouldn't it? Because if it was above ground, it'd have a C value, a starting point, wouldn't it? See where I'm going with that? Is you start to think about what this actually is. Remember yesterday we did the one with the shot put, and like Bella said, the shot put started 5.5 feet up in the air because she was holding on to the shot put. Whereas if you think about the Big Bertha cannon, the cannon, here's the ground. So my cannon looks a lot like something Bugs Bunny would use, but whatever. Yeah. But it's basically, it's like, you ever heard of a bunker? So it's basically, it's just starting underground. Shoots up and goes. So cannon, what goes up must come down, right? Okay. So think about what that means. You have a vertical height and you have a horizontal distance. Okay. I believe the question was, the path shall be modeled by this, where x is the horizontal distance in miles, and y is the maximum height. So if we go to the calculator and try to adjust after we hit graph, we may or may not, mine actually was still in the window from the problem we did yesterday. So it looks like all I have to do is adjust my x value out. So I'm going to hit window. My y maximum is at 25. But my x maximum is at 50. I'm going to change my x maximum to 75 just to see if it shows up. And I'll hit graph again. Perfect. And I can see all of it. Yeah. So do your x maximum at 75 and your y maximum at 50. Hit window. There you go. You got it. Okay. So what we can do here is we're going to calculate 0 like we did yesterday. Remember, there's a button for that. Okay? There's a button for it. So if we hit second calculate, we want to do a 0. Okay? We're going to do 0. So like we did yesterday, we're going to move our cursor all the way over to the right before it crosses over the x-axis. It takes forever on mine, so I apologize. Okay. Now remember what the calculator is doing when you're setting up these, what's called a left-hand boundary or right-hand boundary. What we're doing here is this graph is doing this. We're going to push a button for a left-hand boundary and a right-hand boundary. It's searching within our two x parameters that we set into it, looking for where it equals 0. And the closer you set those things, the more accurate it becomes. Now, we talked about this yesterday. Sometimes you're going to get a different decimal than mine, but you should be pretty darn close. Okay, it should be pretty darn close. So I'm going to hit enter for my left bound. I'm going to go to the right. Remember how we can see once it goes negative? Once that y value goes negative, I know I'm below it, so I'm okay to hit enter again. Guess? I have no idea what that means. Does you ever find out what that means? Why does the 84 say guess? Did anyone ever teach you that? Me either. I always say potato. Yep, that's really all you got to do. It tells me at 69.9 miles, when I round out to 2 decimal places, how far that cannonball shot. That's me. Okay, here's why. You have to do your calculate. So you have to go to second. Calculate, now we're going to do our 0. And now you're going to be, so you have to do your left boundary, all the way right boundary. 74 more sense?
Yeah.
That's why. That's why it's doing that. So I want you guys to think about what that is. In World War II, the Germans had a cannon that shot basically 70 miles. Do you know what's 70 miles that way? Lake Michigan. Seriously, if you shot that cannon from our parking lot, it would land out in Lake Michigan. If you're getting an error boundary, that means your windows are wrong. Okay, if you're getting an error boundary, your either windows are wrong or you set your right boundary on the wrong side of the left boundary. So that's what that means. Now, to figure out the maximum height of this, what button are we going to press for the calculator? Maximum, exactly. So the same idea. If we hit our maximum, second trace, we want to hit number 4, or just scroll to it. We want to get to the left of where it looks like it peaks. Again, I got to hit this button 15 times. It's good times. I hate this emulator. So I'm on the left of where it looks like it peaks. I move to the right of where it peaks. And hit enter a couple times. And there's my maximum, 34.95. At the X value, but the height value is it goes up almost 23.94 miles in the air. 23 point, that's what? Multiply that by 5. That's a lot. That's a lot of feet. Okay. So that's the idea. Okay. Now the other thing that could happen is you knew that 0 is basically at what, 70? So wouldn't that, if we just, let's say we round that to just saying this is 70 and this one started at 0, where's your midpoint? If you had to, could you just throw 35 into the equation and see what y is? You're going to get a rough idea of that. But remember, you've got a calculator. It does this work for you. Okay. Most of the weird numbered ones mirror this same idea. What goes up must come down. How far did something go? How far did something throw? That kind of thing. Okay. Okay. Quilting. Yay, you made a quilt. So quilting, you made a quilt that's 4 foot by 5 foot. You want to use the remaining 10 square feet of fabric to add a decorative border of uniform width. What should the width of the border be? This looks exactly like the first problem we did yesterday in class, where you drew out your rectangle, 4 by 5, and then you wanted to put a uniform bordered width around it. And we called each one of these values something of x, which meant my new would be what? 4 plus 2x, 5 plus 2x. And just like we did yesterday, yes, sir.
Why would it be 2x?
Well, you have border on both sides. That's why. Because what happens here is if you've got, remember we call this border of uniform width? If this is 3, this has to be 3. That's where that comes from. And you're adding it to both sides and up top.
Oh,
That's where that comes from.
I got it.
That's where that comes from. So this turns into an area shaded region problem that you guys did last year. So the area of the overall would have been, what, 5 plus 2x times 4 plus 2x, the quantity, excuse me. And then I had to subtract out the middle area, which was 20. And I had to set the border area then equal to what? Okay. So if we FOIL that out, let's see, we get, what, 20, 10x, 8x, so it'll be 18x plus 4x squared minus 30 is 0. Setting the side equal to 0. You okay with that? So with any luck, we get, what is that? 4x squared plus 18x minus 10 is 0. Now you got two ways of going about doing this. What times what's negative 40 you add together to get positive 18? And I would do it this way because factoring that's pretty easy. You do have a calculator. Could you graph that and find your maximum or find your possible zeros by location and stuff? You can do that as well. It takes a little bit longer. I would steer clear. I mean, when we get to word problem things, you will have calculators at your disposal. Because like I said, you don't want to try and figure out that canon problem without it. Gabe would do it because he's Gabe. But what I would do is I would make sure you guys have those. When it gets to a problem like this, yeah, you can press a whole bunch of buttons, try to figure it all out. But sometimes it's a little bit quicker just to follow the pattern of factoring. So we said what was positive 20, negative 2? And let's do our grouping. GCF, we get a 2x, 2x minus 1, take out a 10. So we have 2x plus 10 and a 2x minus 1. Gives us then our possible zeros at negative 5 and positive 1/2. Which one of those makes a whole lot of sense for a border? 1/2. Okay. Yes, sir. Yeah. Because what's your first term? Is it positive or negative? So it means it is like a. You're right. It's fine. Not all of these are going to be down like a frown. Okay. Not all of them are cannon shots. Sometimes they're up like a cup. Okay. You know. Oh, okay. Okay. Do. Ooh, what? Yes. Yeah. Oh, I went over 35 and it got us our height at 24 and change. It was almost 25 miles, I think. Is the Y value, yeah. The height was the Y value there. I said we realized that it would occur at the midpoint because these were our zeros were 0 and basically 70. So we knew that if we just wanted to get a rough idea, we could throw 35 in and get the Y value. Yeah. Mm-hmm. Yep. Are we unfuzzing a little here? Less? I think those are the easy ones. Okay. Aviation. The length in feet of a runway needed for a small airplane to land is given by L.1 s squared minus 3s plus 22, where s is the airplane speed in feet per second. The pilot is landing a small airplane on a runway that's 2,000 feet long. What's the maximum speed the pilot can land? Okay. So they give you in that problem the formula for length of the runway is 0.1 speed squared minus 3 speed plus 22. And they try to figure out what's the maximum speed if the runway length equals 2,000. Set a side equal to 0, throw it in the calculator. So if I set that side equal to 0, I put that in the calculator, I type it in, I'll get 1. I'm going to use x, is that okay? Because my s's are awful. I get 0.1 x squared minus 3x minus 1,978. And I want to find the maximum of that, don't I? Why would you want to factor that? That'd be awful. You're a nerd. Did you really factor that?
Yeah.
Really? You know what? I'm impressed. Nice job. Still, that's awesome. Good for you. I would never have done that. I would have said, nope. So I would have done this, 0.1 x squared, was it minus 3x minus 1978, what's it guys? I'd hit graph. Obviously my window is a little bit messed up here. Okay. So I gotta find it. We don't know where it is, do we? It's okay, because we don't know where it is. We gotta find it. If I'm not mistaken, if we hit the button that says zoom, isn't there one that says zoom fit? Zoom fit. Let's try that, 0. Hit the button that says zoom, and then hit 0. Zoom fit will allow us to see where the vertex is. Okay, that at least gives us a starting window of adjustment. Okay, does that make sense? So let's see. The obviously, if we're down here, that's our vertex. It's not looking for, if we're trying to figure out how fast can this plane land where it's safe. Well, our speed is our x-axis. I need to figure out where it crosses the 0 so that way I know I'm landing on the ground. Where does it equal 0? The x is going to equal 0 when I calculate, oops, sorry. It's going to calculate 0 when I hit that right there. So what I want to do real quick is trying to readjust my window. Why, good morning. Good to see you. I'm going to hit my button that says window again. And it gave us an x maximum of 75. I'm going to adjust that to be 100 and make my y maximum. That seems weird. Should have been over at 0. Let me change this over to 0 real quick. Unless I type something in incorrectly. I think it's. I'm sorry, guys. Let me go back to zoom fit here. See what my window is showing on this one. You know what? While we're on that zoom fit, let's just hit calculate 0. See what it does here. I forgot if the zoom fit messes it up. So hit your 0. Okay, we're okay. It's very fun pressing buttons like this. A 0. I'm trying to figure out where it crosses the x-axis. Why is this not showing up there? Oh, I gotta go way more. Okay, that's why. I thought this was the x-axis here, guys. This is definitely not the x-axis. We really have to adjust the window. Okay. So let's do our x maximum to be 200 and our y maximum, we'll put it at 10 so that way we're positive, see what happens. Yeah, it looks like I crossed over there. So now let's go back to our, my window for x was 200 max, my y was at 10, so I gotta figure out where it crosses the 0. What button did you press? Did you find a shortcut? Yeah. Yep. All right, so I crossed over there. Okay, cool. So as I'm crossing over the axis, I'm looking for where it goes from positive to negative. Good morning, how are you? Good to see you. Car's being towed. Left bound. See, I've gone positive. The maximum speed that I can go is 156.44 feet per second. What that basically tells you. That's measurements. If you're off a few decibels, yeah, and that's fine because what happens, it depends on how it gets really weird with the calculator where if your window doesn't get set to exactly the same thing that mine has, and then if you set your parameters for your left hand, right hand boundary on some of these, just a little bit off, it could be just, I mean, what did you have for an answer? Yeah, it's close enough. I mean, and that's the thing.
Yeah, I was gonna say mine was like even closer. I had 156.439.
That's what I had. 156.439. 03.
Oh, wow. Even though mine's like in my math like 200 short windows.
And that's it's close-ish, okay? And that's what really stinks with some of these things is that you have to play with the windows to find it. So if you can't find it, zoom fit will get you to the vertex. And then if you know where the vertex is, can't you double in one direction if you have to figure out what the other side would wind up being at? You can do stuff like that. All right, there's that one. What was the other one on that side? 91. 91, 70, yes. We'll do 79 first. Telecommunications for the years 1989 to 1996. I love old data. The amount of billions of dollars spent on long-distance telephone calls in the United States can be modeled by a block, where T is the number of years since 1989. And what year did it reach 60 billion? Okay. So back in my day, we had these things at our houses. What's that? I'm just doing that because it's right below it. So, like I said, back in my day, we had these things in our houses called landline phones. There wasn't this thing called the internet. Some people did have like what are called car phones, where it was literally a phone mounted in your car, like on a stand, and it had a cord and everything. I know it because we had one. It was like really cool. We're like, I'm in my car. And then you have these things called bag phones. You guys ever see a bag phone? Okay, picture Miss Yule's purse. Cut it into 2/3 of that size, maybe, and there's your phone and a battery that you would carry around with you, and it weighed like 37 pounds. I'm on a phone as I'm walking my dog. You know, that's how it was. But the brick phone was even after that. So, but back in these days, you had your local phone service, and then you had to buy long distance phone service because there were two different carriers. So you actually had all these different processes of doing all this weird stuff. So you guys have it so easy. Kids these days. So the amount of money spent was represented by 0.56 t squared plus 0.488 t plus 51, where t is number of years since, was it 1989? All right, so what's year zero? 1989. Okay, year zero is 1989. If you think about it, how much money was spent at year zero? In billions of dollars. No. If year zero is 1989, T is zero, isn't it? So they spent $51 billion. So what we do here is there's another fancy feature on the calculator. When they're trying to find when a specific value occurs, we're going to use the table function. The table function. The table function is awesome for stuff like this. So 0.56x squared plus 0.488x plus 51. And I got to figure out, sorry, I forgot to figure out all my other stuff. Now, if I just hit the second table, everybody see that? Year 0 is the year that it starts. It says since 1989. That means year 0 is 89. Year number 1 would be 1990. Year number 2 would be 91, 3, and so on and so on and so on. Okay? So what we're doing here is they're asking you for about what year did the amount spent reach 60 billion? When does it get over 60? After year 4? What year is that then? So you think about, this is 89, 90, 91, 92, 93. In 1993, spending was over $60 billion on long distance. It's a good year. I graduated high school. Thank you. Yes, thank you. And they actually let me graduate. It was sketchy for a little while there. You know, had to make up like 4 classes. Yeah. I told you I wasn't the greatest student. '80-20, remember? I'm making that one up. I had like 2 classes my senior year. I was so bored. Last one is the firefighter one. And with this one, again, it's a matter of seeing if you can fit it on your window and understanding what does it look like if you are on a ladder trying to put out a fire. A good water stream can be modeled by blah, where X is the water's horizontal distance traveled in feet, and Y is the corresponding height in feet. If a firefighter is aiming a good water stream at a building window 25 feet above the ground, what 2 distance can the firefighter stand from the building? Okay, what? So here's the thing. You have a building window. It's on fire. The building window is 25 feet off the ground. What goes up must come down. So what happens here, if you think about it, if you have a parabola, wouldn't 25 feet touch it at 2 different spots? Wouldn't that give you your 2 different horizontal distances? Let's graph this. Let me show you. Let's graph this. Clear out your y equals negative 0.0, was it point, oops, graph the negative, 0.003 x squared plus 0.62 x plus 3. And then it said 25 feet off the ground. If I do 25 feet off the ground, would y equals 25 just be a horizontal line? Can I figure out where it intersects the parabola then? So let's go to our graph. Obviously, our graph's not going to fit right away. It's going to look awful. Adjust your window. We know we don't need anything negative. We don't need anything negative in y. Wouldn't this be a first quadrant problem? You guys okay with that? Remember when we did stuff like that before, we tried to adjust and try to think about when we were graphing our systems of equations or systems of inequalities. When we did our linear programming, we said, oh, that's going to be first quadrant problem. You can't have negative value. Okay? So in your mind, you start thinking, okay, my window, I know I can have, let's see my minimum at 0. My firefighter hose, my brain tells me it's probably not going to shoot 200 feet, but could it hit 75 feet? I'm just guessing. Okay, I'm just taking a guess. So I'm going to have an x minimum at 0. I'll put this at 75. I definitely don't need a y minimum value at negative 2,000 feet, but I can put And my Y maximum, my vertical height, I need it to at least be 25 because that's where it's going through. So, but I want to see how much the stream does it go up and down. So maybe set it to 50, just to get a rough idea. What we're doing here, guys, is we're trying to use common sense as far as what do you think what could occur with a real world application. And then you just adjust accordingly. Hit graph. Okay. All right, cool. So, and obviously we're on the right track as far as the height. Our height is good, but our distance is short. So we have to add distance to it. Maybe this garden hose does shoot a lot further, or fire hose. So what am I going to change, an X maximum or a Y maximum? X. So we have it right now on our window, our X maximum set to what? 75? What do you want to put it? Double it, go 150, see what happens? Okay, we'll go 200, that sounds good. Yes, sir. Yeah, the easiest way to do it is just restore defaults, and that's your second plus 712, second plus 722. That restores and resets everything. So now, your window isn't the same as ours. Oh, those are the two X values that you would hit. Right, almost done. Sorry. Let's see. On page 3, do those 4. And then on page 4, all right, so there's one box here, one box here, and one box here. Do I see that on page 4? Do this one and this one. Do quadrant 1, quadrant 3. Does that make sense? I apologize, those aren't numbered. On the back page, there's top right, bottom left. And those are like the sales figure style ones. The other ones are straight calculated again. But back to that fire hose thing, what you would wind up doing here, guys, is I'll finish this one tomorrow morning. Your calculator has an option. It says intersect. Everybody see that? You can calculate the intersection, bless you. You can calculate the intersection of those 2 points. You know your Y value to be 25. You're trying to find the X value. That tells you how far away you can be standing from the fire to put it out. Okay? Yes, sir. I did a maximum of an X value of 200. Yeah, we had just changed it to 75 because we didn't see the whole thing. So we were guessing time when we did that. Hey, let's double it, see what happens, and see if we can see, because you want to see where the 2 spots that how far away you can be standing to get it to hit the building. So you can be standing this far away or this far away. You aren't good to hit it. Yay! You hit second, calculate? No problem.